We've just analyzed a terminated transmission line, a length of transmission line that is with the load connected at one end. We applied the boundary conditions and we were able to determine many things in terms of reducing the form of the fundamental functions on the transmission line: voltage, current, impedance, and plus voltage, minus voltage, and reflection coefficient function. Now let's turn and look at the other end of our transmission line. What can we say about the transmission line, or the terminated transmission line rather, based on this end? The first thing to notice that if we take a two-port device, which is our transmission line, and we connect a load to it, a one-port device connected on the end, we formed a new one-port device. And we've talked about this before, having a two-port device with the load connected to it. We can view the two-port device as an impedance transformer, which transforms the load impedance into a new impedance, which is the input impedance. And the input impedance, of course, is the equivalent circuit for the entire one-port device. It is one complex number that comprehends all of the circuit and physical structure of the two-port, both the two-port network and the load at the end. So let's take a look at that. And so we can replace this entire one-port structure, one-port device, with an equivalent value, the input impedance. And once again, I emphasize that this input impedance value is the equivalent circuit for this entire one-port device. It is a complex number at a given frequency that comprehends all the physical circuit behavior of the two-port device. And that, by meaning that, I mean the characteristic impedance, the spatial frequency beta, and the length of the transmission line, in addition to the load impedance. It replaces all of this with one equivalent circuit. So the input impedance doesn't describe, what's going on right here at the beginning of this circuit. Again, a lot of times students think the input impedance somehow describes only this first part. The input impedance, again, is the equivalent circuit for the entire one-port device. In this case, a one-port device that's parameterized by three real values, Z0, beta, and L, and one complex number, ZL. So how do we determine the input impedance of this device? Remember, the input impedance is a complex number which is equal to the ratio of the input voltage, the port voltage at the input of that one port device, divided by the current flowing into that one port device. Now remember, this doesn't mean that the input impedance is determined by Vn or In. It means that the input impedance constrains the ratio or the relationship between Vn and In. V and In can be any complex values, but their ratio must always be equal to this value Zn, and Zn is dependent only on the physical characteristics of the one port device. More importantly, all of the physical characteristics of that one port device. So how would we determine Zn? Let's see if we can determine Vn and In. Now we can determine the input voltage and the input current with knowledge of our one-port device, our terminated transmission line. And of course, we know the current and voltage at every location along that transmission line to within a complex constant V0 plus. We can relate that voltage then at the beginning of the line, at Z is equal to minus L, to the input voltage using KVL, and clearly by KVL Vn is the voltage at the beginning of the line, right here at the index Z is equal to minus L. Likewise, the current, In, is equal to the current here at the beginning of the line, at Z is equal to minus L. Again, I'm point out again, I'm not saying that In is equal to the complex total current I. I'm saying In is equal to the total current I when evaluated at this specific position index. By evaluating the function of current with respect to Z at one location, we turn that function of Z into a complex number which is equal to In. We can then use these results to determine the input impedance. Therefore, we can determine the input impedance being the ratio of Vn to In by KVL. Vn is equal to the transmission line voltage when evaluated at the beginning of the line at Z is equal to minus L. Likewise for the current. The ratio of those two values then is our input impedance. Now, similar to what we did when we evaluated the boundary condition at Z is equal to 0, we recognize that the ratio of the total voltage to the total current is, in fact, the line impedance function. And so we recognize this as the line impedance. Now, does that mean that the input impedance is equal to the line impedance of our transmission line? Of course, that cannot be true. We're saying that the input impedance is equal to the line impedance function when evaluated at the beginning of the line. The input impedance is not equal to the line impedance. The line impedance is a complex function of position Z, where the input impedance is simply a complex number. By taking this complex function of position Z and evaluating it at one specific location, whatever the value of minus L is, that converts it into a complex number equal to Zn. And I point this out because frequently I have students telling me that the input impedance is equal to the line impedance function. And again, it's not. We have to evaluate it at one specific value in order to give it the complex number, which is equal to Zn. So in summary, the line impedance function is a complex function of position Z, whereas the input impedance is a specific complex number. It cannot be a function of index Z. So make sure that you understand that. And the reason I'm emphasizing this is because I see so frequently that mistake made. So let's do that. Let's take our line impedance function and evaluate it at the position index Z is equal to minus L. Recall this is our line impedance function with gamma L in there. Gamma L, of course, we know is the difference of ZL and Z0 divided by the sum of the two. We insert that in there, we get this relationship, or if we use Euler's equation, we can write this relationship in this way. So all three of these expressions are correct with respect to the line impedance function. We can use any of them. What we want to do is take one and insert the value now of Z, position Z is equal to minus L. And notice each of these is a function of position Z, and that shows up in the complex exponential or in these trig functions in the third of the expressions. We do that and we get these expressions here, and they look very much like what we had on the previous page for the line impedance, but of course instead of having the line impedance a function of position Z, we evaluated one specific position minus L, and so notice where we had L before we have Z, but it's, I'm sorry, before we had Z before, rather we have now L, but it's beyond that. We have replaced Z with minus L. And so if you go back and look on the previous page right here with line impedance, for example, this complex exponential was e to the minus j beta Z. When we insert Z is equal to minus L in there, then we get e to the minus j beta times minus L. And of course the minus signs cancel out to give us a positive sign. Likewise, for this term on the previous page for line impedance, we had e to the plus j beta Z, but we insert minus L for Z, and now we have a minus j beta L. So be careful of the signs. This is a mistake that students make frequently. Effectively, they replace the value of Z in the expression for line impedance with L, but again, you have to replace it with minus L. That is the index for the location at the beginning of the line. So be careful of the signs, that they are different once we evaluate it at minus L. The most important takeaway, though, from this result, from the input impedance, is clearly this result is not equal to the load impedance. All right, the input impedance is not equal to the load impedance. Clearly, that is not the case. Moreover, the input impedance is not equal to the characteristic impedance of the transmission line. Now, there can be cases where it turns out it is numerically equal to Z0, and that happens when terms like this become 1, which can happen, but in the general case, the input impedance is not equal to the characteristic impedance. Clearly that is the case. Instead, the input impedance is some complex number. What we'll show is this literally can be any complex number. It can be a complex number with a magnitude of 0. It can be a complex number with a magnitude of infinity. It can be a complex number that's purely real. It can be a complex number that is purely imaginary. So input impedance really can be anything for a terminated transmission line. It just depends on the characteristics of that transmission line, its length, and most importantly, the load impedance that is connected, that terminates that line. Again, don't make these mistakes. I see this a lot. The input impedance is equal to the characteristic impedance of the transmission line, or the input impedance is equal to the load impedance. This is what we might think if we were back in freshman year and we saw these wires. We'd assume the input impedance is equal to ZL. But remember, our transmission line is a big hunk of reactance, inductance, and capacitance. And that's what transforms the load impedance into an input impedance that is far different than the original load. So to summarize that here, the input impedance is, again, different than the load impedance, generally speaking. The real part of the input impedance is different than the real part of the load impedance. The reactive part is different than the input impedance is different than the reactive part of the load impedance. Again, don't assume that this is equal to ZL, and don't assume this is equal to Z0. There are some special cases where that can occur, but generally speaking, they don't. So we shouldn't be surprised that the input impedance is very much different than the load impedance, because remember, the input impedance is simply the line impedance when evaluated at the beginning of the line, at position Z is equal to minus L. And the line impedance, of course, changes dramatically as we move along a transmission line. Here's a plot of the line impedance along our transmission line. Position Z, index Z, is the horizontal axis here. At Z is equal to 0, that by boundary condition we know is the load impedance. The blue curve is the real part of the impedance, and the red is the reactive part of the impedance. At Z is equal to 0, we get a value of 4 plus J0. So the load impedance here must be equal to a impedance of 4 ohms. As we move away from the end of the line back toward the beginning, what we see is our line impedance changes as a function of position. Again, that's the key thing. Our line impedance is different at every location on the line. Both the real part changes, in this case it drops, and the imaginary part changes as we move along the transmission line. A couple of things are interesting here. First of all, notice that the real part of the line impedance is always positive. And of course, a negative resistance would imply an active device, something that would supply energy as opposed to absorb it. So this is something that physically must be true. The real component must always be positive. Conversely, the reactive component, the red curve here, is a value that for half the positions are negative and half the positions are positive. What sense do we make of that physically? Well, a positive reactance, of course, is indicative of an inductive reactance, and a negative reactance is indicative of a capacitive reactance. And so the reactance changes from inductive to capacitive. At some point, notice the impedances are, the reactance rather, is exactly equal to 0. And so therefore our line impedance would be purely real at those locations. Finally, notice at some places on the transmission line, the magnitude of the line impedance function, and that's plotted here in gray, the magnitude peaks up to a maximum value. At other places, the magnitude is at the lowest value. And what we'd find is if we looked at the magnitude of the total current and voltage, the places where the the magnitude is the smallest, the current would be the largest. The total current would be large, and the total voltage would be at a null. The places where the line impedance peak up to a maximum value are the places where the current is the smallest and the voltage is the largest. The input impedance is just whatever the value of this line impedance is at the beginning of the line. Of course, that depends on the length of the transmission line. If we were to have a transmission line that had a value of 0.25, all right, then the input would be right here, and the impedance rather would be a value, looks like, of around 0.5 real and 0 imaginary. If we had a transmission line length that was, let's say, 0.4 meters, it would the input impedance would simply be whatever the line impedance is right here at a index z of minus 0.4, and so there we would see that it would have a reactive component, a positive reactive or inductive component, in addition to a resistive value. So what happens is when we terminate a transmission line with a load, we have determined the line impedance function everywhere on the transmission line. The input impedance then is simply determined by whatever the length of that transmission line is. Whatever the length is, the line impedance at that point at the input is mathematically the input impedance of that resulting one-port device, a one-port device which is a two-port transmission line terminated by some load.